if you look at the end of chapter 10.7 where they talk about Taylor series and Maclaurin series, they have this nice table which summarizes some of the functions that have nicely behaved Taylor series that we have looked at thus far. So we already derived in the videos e to the x and sine of x. 1 over 1 minus x and 1 over 1 plus x are just variants of geometric series. And then from those you can derive formulas for log 1 plus x and arctangent of x. And cosine of x is one that we didn't derive, but it follows a very similar sequence of steps to the sine of x. And then the very last one here is what's known as the binomial series, and that one is a little bit different. I don't know that we're going to necessarily talk about that one in this class, so I wouldn't worry about it too much. But it is a very useful series for a wide variety of problems. Okay, so these are a bunch of Taylor series that we know. And once you've got these, you can use them as building blocks to find other Taylor series or Maclaurin series without having to do all of the tedious steps required to derive the series in the first place. So what I want to do is I want to look at some examples of that. And so I'm going to lock this over to the side of my screen. And maybe we can make that just a little bit bigger. Okay. And let's see if we can do that. Okay. We can make it even bigger than that. All right. So suppose we wanted to find the series, a power series representation for the function x squared e to the negative 2x. Okay? Now, if you were to just try to take a whole bunch of derivatives of this function, as the Taylor series formula requires, you're going to find that the pattern is quite complicated and difficult to identify. But if we can relate this to a known Taylor series, we may be able to get to the power series with a lot less work. So notice, in this case, this is just, you can think of that as x squared times e raised to the negative 2x. And if we think of it that way, then we can take what we know about e to the x and apply that to find the series. So let's think about that. E to the x is the sum from n equals 0 to infinity of x to the n over n factorial. All right? What that means is e to the negative 2x must be that same series. The only difference is we've replaced the x's with negative 2x's, and so we'll have negative 2x to the n over n factorial. Or you could even write that as the sum from n equals 0 to infinity. We could pull out a negative 1 from the numerator, and that would come out as a negative 1 to the n. And then we'll have 2 we could also pull out, 2 to the n times x to the n. And there we go. Now we've got a Taylor series for e to the negative 2x. And if we want x squared e to the negative 2x, all we have to do is multiply both sides by x squared. And so we'll have negative 1 to the n, 2 to the n, x to the n. And since that is just a sum, we can distribute x squared to each individual term. And we'll have the sum from n equals 0 to infinity of negative 1 to the n, 2 to the n. And now we just have 2 extra factors of x. So it'll be x to the n plus 2 over n factorial. So there we go. We've got a Taylor series for a new function, e to the negative 2x times x squared. All right. Let's try, how about the log of 1 plus x squared all over x. Let's find a series for that one. And notice we do have a nice Taylor series for log of 1 plus x. That is the sum from n equals 1 to infinity of negative 1 to the n minus 1 times x to the n all over n. And we want not the log of 1 plus x, but we want the log of 1 plus x squared. So all we need to do is replace the x's with x squareds. And x squared to the n is just x to the 2n, x to the 2n, yeah. So there we go. We got a power series for log 1 plus x squared. If we actually want that function divided by x, we'll just divide by x on both sides. And that's the same thing as multiplying by x to the negative 1. And so we can write this as n equals 1 to infinity of negative 1 to the n minus 1 times x to the 2n minus 1 over n. All right, so using these sort of shortcuts where we already know a Taylor series for a related function and substituting in will allow us to not just transform the geometric series, but transform series for e to the x, sine of x, cosine of x, and any other function that has a known power series.